Good afternoon, everyone. My name is Adam Smith. I'm a technical director within the bridges design team at Arcadis. I've been with Arcadis for 15 years and recently spent a few years with our bridges design team in Bangalore, where we focused on advancing our computational design capabilities. Like most design consultancies, we are navigating a wave of new technologies and digital opportunities. So finding ways to practically implement those digital solutions can be challenging, but also very rewarding. Accessibility and management of data is at the heart of these new processes and technologies. And data-led design is a term used to describe the journey of data through our delivery design process. So I'm going to use my 20-minute time slot this afternoon to discuss part of that data journey. And we'll stop off along the way to give some examples of data being leveraged in relation to the bridge design and asset management, looking specifically at data capture, automation and analytics. So starting off with a quick overview of future trends. Access to data, along with digital processes and tools, are increasingly impacting our industry. So as we march into the digital future, we are all searching for ways to leverage technologies at various points of delivery, from site exploration and geospatial data capture, through rapid engineering modeling and visualizations with AR, VR, to cost and construction management. So management of data is considered to be key to unlocking efficiencies, automation, and better design outcomes. Platforms will link design partners and clients with digital ecosystems. Clients expect early insights and tools to assist with investment decisions. And linking of data and processes will enable more automation and ultimately generative type design processes. And we will need to work with our partners with different specialisms where the end result is greater than the sum of the parts. So these new technologies are already being utilized to great effect in the building space. There's much more potential for bridge design consultants, contractors and asset owners to capitalize. At the heart of all of this is a desire to enhance client and end user experience. Data can help us predict our design outcomes and ensure those outcomes meet the challenges and expectations of the modern world. So I'd like to share a data map, bit of a schematic, with various touch points data has within the design, construction and operation lifecycle. At the front end, we have geospatial data capture, where we have access to increasingly advanced and mobile scanning technologies. Scan to BIM is becoming the norm, alongside image recognition and feature recognition. Historic data capture. Many of our clients and even our own businesses have data locked into inaccessible archives and can be released into this data journey. We now have Internet of Things. Our bridges will join this virtual network as remote structural monitors become more common. The data that we can capture will enable live health checks and will help us understand performance and benchmark against our designs. Automation will be a common theme through this journey, with a particular focus for bridge engineers in the field of design solution development, parametrics and computational design, if you like. So data analytics is at the end, along with other data touch points, but analytics will help us gain insights which can inform our decisions earlier in the design process. So BIM underpins this journey, ensuring increased flow of interconnected data. Standard BIM processes support collaborative technologies that enable data capture and exploitation and give project participants the ability to access and share current, up-to-date, structured and assured information. So I'd like to talk, first of all, or give an example of data capture. At Arcadis, a notable innovation to our approach to data capture has been our bridge inspection projects. And we're using different reality capture technologies. Many of our projects involve capturing data of existing assets and digitizing them for the BIM environment in order to plan and design accurately and efficiently. The different technologies we have used range from simple camera-based photogrammetry, terrestrial laser scanning, mobile SLAM-based scanning, vehicle-mounted LiDAR, and UAV and drone surveys. So with each project being different, we tailor our solution based on the project's requirements. I can share one example where we were commissioned to undertake a headroom clearance check on over 50 bridges in Edinburgh. UK standards require regular periodic headroom checks to protect road users and structures. Current measures for headroom clearance verification involve road closures and manual measuring. And this can be expensive and disruptive to traffic and is often inaccurate. So Arcadis took on the challenge to measure all bridges digitally, allowing headroom clearances to be checked off-site, and the bridges were scanned using state-of-the-art mobile scanning laser technology. A semi-automated process was used back in the office to analyse the bridge geometry using point cloud data captured on site. This process automatically finds the lowest headroom point without needing to manually review numerous cross sections. Vehicle simulations were also used to account for vehicle geometry and approach slopes. So these optimised workflows and processes ensured the task was delivered quickly into a very high accuracy, and using this kind of data capture technology will allow us in future to significantly exceed our clients' expectations. Paired with photogrammetry and augmented reality applications, we are now able to present our clients with data-rich deliverables, which allow a full engagement with an asset from a remote location. So back to the data journey. Data is being captured more easily, it's becoming less siloed, and creating data hubs or common data environments forms the basis of a data-led design process. The natural progression within the data-led design process is to automate. And that is what I'd like to discuss next. As part of our 100% BIM strategy, Arcadis is pursuing a range of digital design capabilities, increasing sophistication of the software and hardware. And the way in which we use it allows us to embed more efficient workflows, which deliver new solutions for our clients effectively and quicker than before. So we've all been applying parametric automation for a long time in Excel spreadsheets and our analytical packages, but we're increasingly using parametric tools which significantly extend the reach of these processes, enabling data to flow between different software and databases. This graph illustrates our trajectory along the automation path, and right now we are building skills and finding opportunities to apply parametric computational design. This will ultimately lead to opportunities for generative design, where we describe our end goal and use automated data-led design process to find the optimum solution. The goal here is to make our design process much more efficient, but also it is essential in a BIM environment to provide the necessary flexibility to adapt and optimize and find the right solution. Without automation, it is too easy to become fixed at a non-optimized solution early in the design phase. And the first design model that is created can unduly influence the end deliverable due to perceived pain, if you like, in changing and adapting. As structural engineers, the opportunity to apply parametric data-driven design automation is very exciting. And I'd like to share an example of how we are currently applying this process on one of our larger schemes. So as a multi-structure scheme, HS2 lends itself to standardization and automation opportunities. A standardized approach is also essential to ensure a consistent deliverable across the design teams. So the automation challenge for bridges and bridge teams normally focuses on two interlinking deliverables: the 3D geometry creation and associated asset and element data, the BIM model, if you like, and the analytical model as well, which informs the structural design. So in theory, any design process can be automated, but significant variability in the potential design outcome will result in a tool or process that is too complex and time-consuming to develop. To successfully automate, we need to standardize the design process and reduce the number of potential branches on the design decision tree, if you like. The first fixed decision might be the type of bridge you're planning to design. From that point, the team can begin to rationalize the design process and build tools to complete certain design tasks. Mapping out the design workflow is the starting point for any automation effort. A clearly defined process with correct assurance and governance avoids wasted effort. The data itself must be codified and classified consistently so that it can be compared and integrated and is recognized and accepted by our technology systems. Modern engineering projects produce enormous amounts of data in a multitude of formats, and it's certainly the case on HS2, such as models, drawings, schedules, documents, and more in numerous different native softwares. This data needs to be accessible to engineers in the design infrastructure assets, in the design of infrastructure assets. All of this disparate data is pulled into the master database through data handlers, which convert and standardize the information into a common format. The data is further processed through bridge designer applications until the database contains all data points that define the particular bridge being designed. Setting out of the bridge is defined by a set of complex rules and relationships which can be repeated across structures of similar type. Defined rules are also in place for detailing of the individual bridge elements, which align to the codified and client-defined specifications. The design forms can be described as the structure DNA and are relatively software agnostic at this stage. It's from this point that the model-based digital deliverables are developed. Parameters stored in the design forms unlock the opportunity to automate and rapidly produce complex deliverables of many types. The forms can be read by computer software scripts, and this unlocks the capability to automate production of reports, calculations, analysis, and BIM models. So once our design is complete and construction is complete, we will hand over this data as a digital twin, providing a complete digital replica of the finished railway to support its ongoing operation and maintenance. Developing these processes takes significant investment, but multi-structure schemes provide the opportunity to put design automation into practice at a high level. Clients now expect an advanced and data-rich delivery, and in many ways, this is not possible to achieve without automation. Manual production of BIM models can be a time-consuming and risk-prone business, and the vast amounts of data that is embedded and extracted from these models cannot realistically be managed using manual data handling procedures. In this case, the computational design team has built programs which connect the design form and read all the necessary parameters. Further parameters are newly defined as the model is auto-generated. For example, the track orientation and clearance requirements along the highway alignment enable the scripts to find a best fit for the deck, optimize spans so that they match precast parapet 3-meter length increments, and also match a set range of beam lengths and maximum gradients. In addition to design optimization and geometry creation, the tools assist in tagging and extracting attributes from each bridge element. There are typically 150 elements per bridge, with up to 150 data attributes per element, essentially over 20,000 pieces of data per bridge. Manual creation of this seemingly simple design and associated model would be extremely challenging and takes weeks with very little scope to change. The parametric automation tools, once established, enable a more accurate model to be achieved within 5 minutes, with the ability to change and optimize if the opportunity arises. These tools are doing more than simply translating geometric parameters into digital models. They are augmenting the design process itself, providing early insights and enhancing the application of engineering expertise. So we've seen how data capture technologies and automation is opening up opportunities to deliver data-rich deliverables to our clients. But the data journey continues, and we are now exploring ways to predict likely outcomes and performance through data analytics. At Arcadis, we have dedicated data analytics and data science teams with expertise in data management, data visualization, robotic process automation, and application of Internet of Things. With properly managed data as a foundation, we are able to power predictive and prescriptive actionable insights for our customers. One example includes the application of machine learning, image recognition technology, and predictive analytics to automatically survey road pavement conditions in the UK and predict deterioration over the next 5 years. This enables our clients to focus budgets and plan road closures to minimise disruption. Digital twin type monitoring technologies are being implemented for existing bridge assets, including the Surhof Bridge in the Netherlands, where an optical monitoring system linked to finite element models is helping predict bridge performance. In simple terms, we are able to use predictive analytics to measure the likely outcome and ongoing performance of our designs and existing assets, measured against key performance indicators. Accessing and learning from our own historic data is something the Bridges teams are currently focusing on, and you can see an extract from our Bridges database app, where we can rapidly interrogate existing bridge data and benchmark new designs. This type of analytics will enable engineers in future to demonstrate constant improvements to clients, particularly in terms of optimized material use and reduced carbon footprint. And this can be applied to all types of data sets. So looking at the data flow again, in the context of data-led design, we were able to see how the predicted outcome can inform the design much earlier in the process so that we can optimize. Our data sources are collated within a common data environment, and we can see how data capture technologies can provide an almost instant digital environment in which to deliver our designs. Options are developed based on defined performance criteria. Models are federated and deliverables produced, but instead of waterfall type delivery process, as we can see here, the data goes full circle. Automation provides design flexibility and accelerates the data feedback loop so that designs can be optimized and alternative solutions offered to our clients early in the design phase in a timely manner. By implementing a systematic approach to our design process, we can move towards computer-generated solutions that are optimized towards our clients' needs. So in summary, we've seen the data touch points through the data journey. With data capture, safe and portable mobile mapping solutions, opening up opportunities to deliver more enhanced solutions for our clients. Scan to BIM, enabling rapid digitization of our environment. And Internet of Things, providing vast sources of data. Automation will reduce manual handling of data. We have an ability now to adapt to change and optimize. This enables us to focus on the engineering rather than the model production. We've also seen how analytics can provide insights, and early insights are very important in the design delivery process to ensure that we can deliver a better outcome for our clients. The data analytics provides a glimpse of the future. We can have outcome-driven solutions and greater cost control, and virtual construction, removing risk of unknowns. So this is all focusing towards improved client and stakeholder experience. We will be able to deliver consistent quality deliverables aligned to client requirements. Industry data standards enable a fully integrated supply chain, and industry-wide efficiencies can be driven to align to government targets for 2025. I hope that's been an informative run through of the data journey. I know I have only touched on a few points, but I'd welcome any questions.